The first problem, I think this is this we had seen already, right? What is the first one? The configuration of cascade amplifier is CE and CB. CE and CB. Therefore, what is the answer? Which we had seen already in the last class. Answer is B. Okay. Second problem. The quotient collector current IC of a transistor is increased by changing resistances. As a result, okay. What is saying? If you take any circuit saying that your IC is increased, when IC increases, then what will happen? GM will not be affected, GM will increase, GM will decrease, GM will increase or decrease depending upon bias stability. Okay. You take common emitter amplifier or anything, then tell me what is your GM? Your GM is nothing but IC by VT, right? Therefore, if IC increases, then what will happen to GM? Your GM also will increase. Therefore, what is the answer? C. Answer is C. Now, problem number 3. What is problem number 3? Each transistor in the Darlington pair, which is given below, has HFE is equal to 100. The overall HFE of the composite transistor, neglecting the leakage current, is, okay. Therefore, what is the circuit? This is what is Darlington pair, 2 CC amplifiers. This is what is your maybe composite transistor, you can say. This is what is your overall collector, you can say, and this is what is overall base, and this is what is the overall emitter. That is what he told, right? This is what is your composite transistor having 2 stages. This is what is equivalently a block for you, right? And this is what is our collector and then emitter, and this is what is our base, composite transistor terminal. Okay. Then this is what is having HFE, and this is also having HFE. Now he is asking what is overall HFE of this. Okay. HFE of your composite transistor. First of all, what is HFE? We know that HFE is nothing but your output current. Your output current divided by input current. It is basically your gain, your input current, right? Therefore, when I say this is what your output current and this is what your input current, right? Therefore, what is that output current of your composite transistor? Right? Tell me what is your output current here. Therefore, what is this current? This is nothing but your, let us say your IC, then this is nothing but your IC1, then IC2, right? Now, saying that this is what your IC1, therefore what is the HFE? This is nothing but your IB1, which is nothing but your, then this is nothing but your IB2. Your IB2 is nothing but what? Your IB2 is nothing but approximately IC1. Let us take that is what is approximately equal to IC1. Therefore, tell me, therefore what is your IC1? Your IC1 is nothing but HFE into IB1. Therefore, instead of representing your what do you call capital letters, because we use small letters for HFE, therefore this is what is your AC current, and this is what is your AC current IB2. Therefore, tell me what is this? This is what is your IC1. What is IC1? Your IC1 is equal to HFE into IB1. That is what you can say. Then what is your IC2? Your IC2 is equal to what? HFE into IB2. Right? Therefore, what is our? We know that from the circuit, we know that what is IC2? Your IC2 is equal to HFE into IB2. What is IB2? What is IB2? Your IB2 is nothing but IE1. This is nothing but IE1, right? This is nothing but your IE1 with respect to this. This is nothing but your IE1, right? Therefore, this is nothing but IB2 is nothing but your IE1. What is IE1? IE1 is nothing but IC1 plus IB1, which is nothing but HFE into 1 plus beta, right? Or 1 plus HFE into IB1, which is nothing but HFE into 1 plus HFE, and this is what is your IB1. That is what your IC2, right? Then what is your IC1? HFE into IB1, right? Therefore, what is your output current? This is what it is, right? Now, what is your output current? Therefore, overall HFE, therefore you can say HFE dash. Therefore, overall HFE is equal to what is your output current? IC1 plus IC2. IC1 plus IC2 divided by what is your input current? IB1. Therefore, what is IC1? This is what your IC1 plus what is your IC2? Therefore, IC1 is nothing but HFE into IB1 plus what is your IC2? HFE into 1 plus HFE into IB1 divided by IB1. Therefore, this is nothing but, this is new HFE. Therefore, this is nothing but, if you take IB1 common, HFE plus HFE into 1 plus HFE. Actually, you can neglect this HFE with respect to this. Okay. But anyway, this is the exact value. Therefore, what is HFE given? HFE is nothing but what? HFE is nothing but 100. Therefore, 100 plus 100 into 101. What is 100 into 101? This is nothing but 100 plus, can I write it as 100 into 100 plus 1, then it is 100 into 100, 100, 200. 100 into 100, 10,000 plus 200, you can say 10,200. Therefore, what is the answer? Answer is D. Therefore, answer is, this is what is your new HFE. Write this. Then we'll see problem number 4. I hope everyone understood, right? Yeah. This is composite transistor. Then with respect to that, this is what is your IC. Therefore, this is what is your IC, where IC is equal to IC1 plus IC2. And this is what is your input current IB. That IB is nothing but IB1 only. Therefore, your HFE is nothing but This is what is having your new HFE. This is what is having HFE dash. This is what I call it as HFE dash for the composite transistor, which is nothing but your output current IC divided by IB. Therefore, IC is nothing but IC1 plus IC2, and then IB is nothing but IB1. We know IC1 is nothing but HFE into IB1. Then IC2, we already calculated what is IC2. IC2 is nothing but HFE into IB2. What is IB2? IE1. What is IE1? IC1 plus IB1. That is what we did it. Then we got it. Remember, if you take IB2 is equal to IE1, and then if you assume that IE1 is equal to IC1, then you will not get this one. Then you will get, this is 10,000 plus 100, 10,100. That option is also there. Very important. See, then can you go for approximation, where you can take IE is equal to IC. That depends on the options also. If you see the options A, B, C, D, C and D are close by, what does it mean? Then we need accurate answer, not approximate answer. Okay. Strictly speaking, your IC, right? IC is equal to HFE into IB and all those things. If you take AC currents, the saturation currents can be neglected. But if you take DC currents, then your HFE is nothing but your beta. Then in that case, you cannot say, because he told that reverse saturation currents can be neglected. Because if you consider DC, IC is equal to beta into IB plus 1 plus beta into IC naught. If you neglect that reverse saturation current, then only your HFE will be beta. Else HFE is not equal to beta. Remember. Okay. Therefore, because you didn't say anything about DC and then AC, therefore, in this case, if you neglect reverse saturation current, then your HFE or beta both are same. Okay, fine. Done, right? Let's solve problem number 4. Problem number 4. The transistor in the amplifier shown has following parameters: HFE 100, HIE 2 kilo ohm, HRE 0, HOE 0.05 millimos or 1 by ohm. C is very large and output impedance is, therefore is it AC analysis or DC analysis? Because we are asking what is output impedance. Therefore if it is output impedance, surely this is what? AC analysis. If this is AC analysis, wherever there is a capacitor, that's why he has given that C is very large. Means for small signal, for small low frequency also, you can treat capacitor as short circuit. Therefore he said that for any signal which is having some change the frequency component, you can treat that as the capacitor as short circuit. Then if you treat your capacitor as short circuit, and then if you take AC circuit, therefore if I take AC circuit, then what do you get? This is what is your short circuit, Then this is what is your, this is nothing but your 5K, right? This is your RC. RC is equal to 5K, and this is what is your output voltage, and then AC ground actually. Then I don't need to bother about this, and this is what is your VI. Okay, shorted. Don't need to take anything. That's it. Okay, this is what your collector, emitter, base. This is what is your AC circuit. Actually, we have R1, R2, VCC, right? VCC is connected to ground, AC ground. Then this is R1 is coming in parallel to R2. That is coming in parallel to your input voltage. Voltage source in parallel to resistor is nothing but a voltage. Therefore, you can ignore that R1, R2 combination for AC analysis. That is having significance in DC analysis. Okay. Now, we need to calculate. Therefore, asking, when I say this is what your amplifier, if you say this is what your amplifier, asking when you have AC load here, asking what is output impedance. This is what is your output impedance R0. Okay. But remember, when we do BJT AC analysis, that time I told that whatever which is connected to your transistor, that you consider this as a load. But now with respect to your actual DC load, but remember this is your biasing resistor, DC biasing resistor. But with respect to actual AC load, because we have AC cap and the load, this is your actual AC load. With respect to that load, now if you treat this as an amplifier circuit, asking for what is output impedance. Therefore, whatever transistor output impedance you have in parallel to the 5K, that is what your effective output impedance with respect to your load. Remember, that is what is very important. But whatever formula or whatever we derived before, that is this output impedance, the transistor output impedance. Therefore, maybe let me call this as R0 according to our notation, and this is what is our R0 dash. Let us say this is what we need to calculate, which is nothing but R0 in parallel to your RC. This is nothing but your R0 in parallel to 5 kilo ohm. Let's see what is this value. Okay. Therefore, what is R0? First of all, what is this configuration? This is common emitter amplifier. This is CE amplifier. Tell me what is output impedance formula? We know that Y0. We calculate Y0. What is Y0? HOE minus HRE into HFE divided by RS plus HIE. Go to the theory. What we have seen. We derived this also, output admittance, right? Therefore, but he has given HRE 0. When HRE is 0, then it is simply HOE. Then what is your R0? Your R0 is equal to 1 by Y0. Therefore, 1 by HOE. Therefore, what is HOE? It is given 1 divided by 0.05 milli. That milli will become kilo. Kilo is nothing but 1000 divided by 0.05. Therefore, what is 1000 divided by 0.05? 520, right? 520. Okay, how will you write? Can you write this as like this? 10 to the power of 3 divided by 5 into 10 to the power of minus 2. Then what is 1 by 5? That is 0.2 into 10 to the power of 5. Which is nothing but, if you take 100, then it is 220K. This is nothing but 20 kilo ohm. Therefore, what is our output impedance? 20 kilo ohm. But you remember, if you don't neglect this HRE and then if you take proper HOE and then values, the typical values of H parameters, we remember when RS is equal to 1K, we got output impedance 52.5K. Here 20K with respect to the values which are given. Now, therefore tell me what is your real output impedance. Therefore, what is your actual AC output impedance? Is nothing but 20K in parallel to 5K, surely less than 5K. Therefore, 20 into 5 divided by 25 kilo ohm. 5 5s are 5 4s are. Therefore, it is 4 kilo ohm. What is the answer? See, 20 kilo ohm is also there. to do not confuse you. If you think that this is what your output impedance, but according to the representation of the circuit, if you see asking the impedance, because output is defined here, therefore asking for output impedance, then we have to include this 5K also. That is important point. Therefore, what is the answer? Answer is take this. Then we'll see problem number 5. Done. Write down problem number 5. Of the 4 biasing circuits shown in figure for the BJT, indicate the one which can have maximum bias stability. Okay. Actually, how many bias circuits we had seen? 3 only. Fixed bias circuit, collector to base bias circuit, and self bias circuit. I told that collector to base bias circuit and self bias circuit both are having almost same stability. But due to the final implementation including AC analysis plus DC analysis, the collector to base bias circuit needs what? Inductor. We don't want to use inductor. That's why I told that we go for self bias circuit. Option A, self bias circuit, it is stable. Option B, fixed bias circuit, that is not stable. Option C, self bias plus collector to base bias, it has both. Therefore, it has 2 types of negative feedbacks. Most stable. Option D, only self bias circuit, right? Option A is self bias, option D is also self bias, but option C is having self bias plus collector to base bias circuit. Therefore, option C is correct. But the issue with this is, if you want to bypass your feedback, RE we can bypass using a capacitor, which we had seen. That is what is your self bias circuit. But if you want to bypass, or if you don't want to have negative feedback for AC signals, we need to have in series inductor of RB. That is difficult because inductor is bulky in the nature. What it may be is asking for DC analysis stability. Therefore, that is what answer is C. No need to say. Therefore, which is what is most stable? Most stable out of 4, most stable is self bias plus collector to base bias. Collector to base bias. This is what is having more stability. Therefore, what is the answer? Answer is C. Straightforward. Now, problem number 6. For good stabilized biasing of the transistor of common emitter amplifier, which is shown in figure, we should have, this is nothing but your, okay, C amplifier. Then what is that saying? We should have what? We should have, you see the options. Circuit is given. Circuit is and this is what is our V naught. Okay, anything is fine. And this is what is our V in. This is what is our V naught. Okay, this is what is given. Now option A, RE by RB very much less than 1. Option B, RE divided by RB very much greater than 1. Option C, RE divided by RB very much less than HFE. Option D, RE by RB should be greater than HFE. Doesn't matter. Now here asking for stabilized biasing. Okay, fine. Basically we want more feedback. Remember, if Q point is more stable, obviously your AC gain is also more stable. Your AC gain is associated to the signal change with respect to time. DC operating point is also what? Signal which is not changing with respect to time, right? If you know the DC stability, which is almost same to AC stability if you don't connect any other component, okay? What that may be? For a DC, is saying that this capacitor is not required. This capacitor is not there. That is what we want, a negative feedback. Now, what is RB? Actually, we have seen this, right? What is that? Now, if you see V Thevenin, R Thevenin, then it is nothing but your, this is nothing but your RB or R Thevenin, which is nothing but R1 in parallel to R2, and this is what is your V Thevenin, because no need to bother with AC signals, only DC circuit. Therefore, this is what is your DC equivalent circuit. Okay, then this is what is our V Thevenin or VB, which is nothing but R2 divided by R1 plus R2 into VCC. Okay, then this is what is our circuit. This is what your RE and RC. This is your VCC, and this is what is your VCE, and this is your IC. For this is nothing but your self bias circuit. This is your self bias circuit, and you remember we solved what? Stability factor. What is stability factor? And we got stability factor, right? What is stability factor? Your stability factor is equal to, you remember, 1 plus beta into RB plus RE divided by, RB is nothing but your R Thevenin, okay? RB plus 1 plus beta into RE. This is what we got. Then we simplified this, right? This is what stability factor which we solved. This is what is your stability factor, the change in IC with respect to IC naught when VBE comma IB constant. That is what we derived. Therefore, now what is simplified form? If 1 plus beta, beta is nothing but HFE. If 1 plus beta into RE is very much greater than RB, then what is your stability factor? Your stability factor is close to 1 plus RB divided by RE. This is what we got. This is what is derived stability factor. This is what is your derived stability factor. Therefore, now tell me, we want stability factor to be as minimum as possible. Ideally, we want stability factor to be 0. Therefore, ideally, we need stability factor to be 0. But practically, right, as minimum as possible. As minimum as possible. That is what we can get, right? Therefore, tell me what is S minimum. The minimum stability factor what you can get from this is nothing but what? That is nothing but what? 1. When? If and only if RB by RE, RB divided by RE is very much less than 1. If RB by RE is very much less than RE, then your stability factor will be close to 1. Therefore, what is the answer? But is asking RE by RB, everything is RE by RE. Therefore, your RE divided by RB should be very much greater than 1. Both are same only. Therefore, what is the answer? RE by RB should be very much greater than 1. Answer should be B. Your answer is B. If this is true, this will be true automatically. Okay, that's fine. Therefore, write down. Therefore, what is the answer? Answer is B. Done? Okay. Write down problem number 7. Problem number 7. Which of the following statements are correct for basic transistor amplifier configuration? Okay. Option A. What is option A? CB amplifiers has low input impedance and low current gain. You remember, I think I gave, right? CE, CC, CB. I think I already gave. If you take the first one, voltage gain we got minus 400, current gain we got minus 40, RI we got 1 kilo ohm, R0 we got 52 kilo ohm. That is when RS is equal to 1K and RL is 10K for this combination. CC amplifier close to 1, AI 40, RI 400 kilo ohm and R0 40 ohm. CB voltage gain 400, current gain approximately 1, RI 22 ohm, R0 1.3 mega ohm. That is what we got, right? Okay, now let's see. What is option A? Your CB amplifier saying that has low input impedance, means RI is low and low current gain. Current gain is low. Is it true? Your common base amplifier is having RI low. Is it low? Yes, this is low. And current gain low. Yes, this is unity. Therefore, this is also low. Therefore, can I say option A is true? Yes, this is true. But remember, he says which of the following statements are correct. Therefore, you can have multiple options. Let's see option B. What is option B? CC amplifiers, okay, low output impedance. Your R0 is low and high current gain. Your current gain is high. Is it true? Your R0 is low. Your R0 is low. Yeah, this is low. And your current gain is high. Yes, this is high. Therefore, this is true. Therefore, this is also true. All are true. Let's see. Now, option C. CE amplifiers has very poor voltage gain. CE saying that AV is poor and very high input impedance. Your RI is high. Let's see. What is AV? Actually, it is high for single stage. Therefore, this is wrong. And what is RI high? It's not high. It is moderate. It is moderate. Therefore, this is false. Option C is not correct. Okay. Now, let's see what is option D. Therefore, what is option D? The current gain of CB amplifier. The current gain of CB amplifier, AI of CB, okay, is higher than current gain of CC amplifier. Current gain of CC amplifier. Tell me what is current gain of CC amplifier? CB amplifier, current gain of CB amplifier is, this is 1. What is current gain of CC amplifier? Let us say 40. Is this true? Is 1 greater than 40? No, this is also false. Therefore, what are the answers? Your answer is A and B. We have two answers. A and B. I'll give you 50 seconds time or 1 minute time. Try to draw. We had seen this already, but remember, don't remember these values as granted when RS is 1K, RL is 10K and typical H parameter values. These are all values. Okay. Done. Write down problem number 8. The bandwidth of n stage tuned amplifier with each stage having a bandwidth of B is given by saying that there are n stages. Number 1, number 2, multi-stage amplifier. Okay, 1, 2, n stage. Each is having a bandwidth of B. Then what is overall for n stages? What is overall bandwidth? Okay, you remember I already discussed. If you take RC coupled CE amplifier, right? Then I discussed about lower cutoff frequency and higher cutoff frequency. As the number of stages are increasing, your lower cutoff frequency is increasing, higher cutoff frequency is decreasing, therefore FL to FH, therefore that is decreasing, your bandwidth is decreasing, right? As gain increases, therefore bandwidth, as gain increases, we know that your bandwidth decreases, that is sure. Therefore, what is your bandwidth now? Therefore, your new bandwidth is equal to, it should decrease with the value of what? 2 to the power 1 by n minus 1. Let us say n is equal to 2. Let n is equal to 2. Then what is this? Your B dash will be equal to B into 2 to the power of 1 by 2, root 2, 1.414 minus 1 root. Therefore, this is nothing but what? This is root 1.4, root 0.4, definitely less than 1. Therefore, it is less than B. Your bandwidth will be less than B. Therefore, what is the answer? Your new bandwidth will be B into a factor. The factor will be less than 1, which is nothing but 2 to the power of 1 by n minus 1. This is what is derived based on hybrid pi model of your BJT. Okay. Therefore, what is the answer? Answer is C. Answer is C. Done. Write down problem number 9. For the amplifier circuit shown in figure, the transistor has a beta of, the transistor has a beta of 800. Okay, the mid-band voltage gain of the circuit will be, so for the circuit is 200K, 100 kilo ohm, 15 volt, and this is 470 ohm. Okay, now option A is 0, option B less than 1, option C close to 1, option D 800. Therefore what is asking? Is asking for V naught by Vi, which is nothing but your voltage gain, mid-band voltage gain. Okay, first of all, AC analysis or DC analysis? This is nothing but AC analysis. If this is AC analysis, we need to consider AC circuit. Remember, this is not NPN transistor. This is PNP transistor. Therefore, this is nothing but what? This is emitter. This is base. This is collector. This is what is our collector. Okay. Therefore, now, actually no need to draw AC circuit. By this time should visualize on your own. No need to draw AC circuit and get it. Okay. Simple. First of all, you should understand the configuration to proceed. Tell me, where are you applying? For AC circuit, capacitor will be shorted. The capacitor will be shorted. This is what is connected to ground. Right? Then this is what you will get like this. Now, tell me, where are you applying your input? We are applying input at base with respect to collector. Where are you taking your output? I am taking my output at emitter with respect to collector. Applying input voltage at base with respect to collector, taking output voltage at emitter with respect to collector. For both input and output, collector is common. For both input and output, collector is common. Therefore, what is this configuration? This is CC amplifier. Whether it is NPN transistor or PNP transistor doesn't matter for us. Okay? CC amplifier. What is voltage gain of CC amplifier? We know that 1 minus HIE divided by RI. 1 minus HIE divided by RI. This is what is our voltage gain. Therefore, we know that it is close to 1. No need to calculate. We know for CC amplifier that is what is close to 1. Therefore, what is the answer? Answer is C. I think time is done for the session. We will continue in the next session, right? We will solve problem number 10 in the next session. Okay? See you. Thank you.